today's lesson, we are going to cover domain and range of a function by looking at the table of values, using some common sense, as well as looking at graphs and equations to find the domain. The table below shows a relationship between circumference and height of a tree as it grows. Determine a reasonable domain and range. Before we do that, we should define that domain is the set of all possible input values of an equation. Typically, these are our x values. And the range is the set of all possible output values from the function, and these typically are our y values. When I'm thinking about the circumference of a tree and its height, it appears as if the height here is dependent upon the function of whatever our circumference is. Therefore, our circumference is going to be the domain, the input values, and our height then is determined on how round our tree is, if you will. So this will be our range. When I'm looking at my table of values, I have a wide variety of both circumference and heights. However, I have to think reasonableness with respect to how wide, with respect to the circumference, is it possible for a tree to have? I did some Googling so that I could rely on my experience and reason to approximate the domain and range. I found, using world records, that the maximum circumference is 119 feet. Thus, our circumference should be greater than 0, but most likely less than 119. And I'm going to say feet. I also did the same thing with our height, and I found that the maximum height was 380 feet. I would also venture that our height would also have to be greater than 0 if we're going to consider a tree. 380 feet as our maximum height. In example 2, when sending a letter through USPS, the price depends upon the weight of a letter as shown in the table. It cannot be over. So our maximum is going to be 3.5 ounces. It can't be over that. And then we're going to let P be our price here. So the price is determined upon the weight. So this is our input, and then P will be our output. We know that we can have a variety of ounces of weight for our letters. I'm going to say that we have to be greater than 0 for our weight, but less than or equal to 3.5, because it can't go over 3.5 in order to do that. We can have weights in between though, but our range is a little different because our price can only be 4 things. It can only be 44 cents, 61 cents, 78 cents, or 95 cents. Doesn't say anything about being in between those. It just, our weight cannot be over a specific load, and then depending upon which 4 categories it falls in, it will land at the price on the right hand side. Now there are 3 different ways in which we can write and describe a domain. We can also utilize these same strategies or same ways to write them when we talk about our range as well. In the line graph, I have that my graph can be between 1 and 3, inclusive, because I have these dots here that are circled, highlighted in. These are included. Whereas this is an open circle, so this will be excluded. And then, of course, an arrow means that it's going to continue on forever into infinity, and we'll talk about that in a second. So in inequality form, my x value has to be greater than or equal to 1, but less than or equal to 3. So x has to be in between 1 and 3 inclusive, or x has to be greater than 5. Notice that I did not put a slash underneath because it can't be equal to 5. It just has to be greater than 5 is where we're starting. Set builder notation will also utilize these same equalities, except I'm going to start with a brace. I'm going to say x such that, so that vertical line means such that our x values have to be in between 3 and 1 inclusive, or x has to be greater than 5, and then I close my brace. The interval notation is the one that is typically used most often. And notice that 1 and 3 were included, so these get to use brackets. And 5 is excluded, so this gets to be a parenthesis. So our interval notation, our x values are between 1 and 3, and then they're included. And then I put a large U, this means or. I'm going to use a parenthesis because it's not included. 5 to infinity. And infinity never is included because, as we know, infinity never stops. And therefore, it has to have a parenthesis because we don't have a definitive ending point. The same is true if you go to negative infinity. You will also have negative infinity have a parenthesis as well. I can also identify domain and range when I'm looking at a graph, just as we have here. I have my x-axis down here, which is the years. And this is going to be our domain. And then it looks like we have barrels. And this is going to be our range. So when I'm looking at my domain, granted, we know that there are more years that are older than 1975. However, this is just with respect to our graph. So our graph looks like it starts at 1975, and it looks like it's going up by 5. So each little tick mark, each one of these little tick marks here is a single year. So this must be 2008. So our years have to be between 1975 included, I'm putting Y for years, and 2008. If I wanted to write it in interval notation, I could put 1975 to 2008, inclusive for both of those. Now our range talks about how low and how high our graph is. So I'm thinking about how low my graph is just under 200. So maybe our graph starts at 180-ish. But we're in barrels. And then the highest mark looks just over 2,000, so maybe 2,010 barrels. Again, I could also put it in to set interval notation as well. So 180 to 2,000, 2010 barrels included. I don't see that there are any holes, so we can assume that they reach that level. And again, those are just our best guess as where the graph ends at. Now, if I want to utilize and find the domain with common functions, in my two functions below, I have both a radical with a square root, and I have a rational function where I'm dividing by, where I could have an x in the denominator that we have to take care of. In these two situations, there's two things to remember. We cannot have negative values underneath the square root sign. So under here has to be greater than or equal to 0. I can take the square root of 0, which is in fact 0, but when I take the square root of things like -4, we end up with complex numbers. So I'm going to restrict my domain because we do not see the complex numbers in the real number system when we're graphing normally. I can solve for this by subtracting 4 from both sides. So I'm automatically given, when I'm doing this, I'm automatically given the inequality version of my domain. But I could also put this in interval notation where x can be -4, but it has to be greater than -4. So we're going towards positive infinity, where we stop at positive infinity, which is non-existent. So it'll keep going, which is why we're using that parenthesis. Now, we also know that we cannot divide by 0. So in this instance, when I have a rational function, I want to make sure that 6 minus 3x is not equal to 0. So to do that, I'll subtract 6 from both sides. Therefore, -3x cannot equal 6. X cannot equal +2. It can be anything but +2. So if we're thinking about a number line, here's +2. It cannot be that, so I'm excluding, but it can be all the numbers to the right and all the numbers to the left. So writing this in interval notation, I can come from -infinity all the way until I hit +2, exclude it, hop over +2, and then I get to continue on to positive infinity. The next type of function that we want to talk about is piecewise functions, because a piecewise function depends upon the domain of the input and where it lies. So we're often given more than one equation and then restrict our domain to determine which equation we are able to utilize. So in this example, a museum charges $5 per person for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for 10 or more people in the group. Set up a function relating the number of people and to the cost. So the cost is going to depend upon the number of people that we have in our group. We had two different pieces. We had $5 per person with a group of 1 to 9, or if we had 10 or more people, it was $50. So it will be $5 per person if we have a group of 1 to 9 people. So we can't have a half of a person. So I'm going to say when my group is between 1 person included and 9 people included. However, it will be $50 if we have in our group the number of people greater than or equal to 10. Because again, we can't have half people. It's okay to jump from 9 to 10 because you can't have 9.5 people in a group. So we just wrote the function relating all those pieces together. Now let's put this type in action. So if I'm given a function below, a piecewise function, determine the cost in dollars for gigabytes. So I'm going to be looking at depends upon how many gigabytes I have will depend upon which of these functions I will utilize. So if I have 1.5 gigabytes of data, 1.5 falls in my first function. Therefore, if I have 1.5 gigabytes, I'm just going to be charged a straight $25. However, if I have 4 gigabytes, I need to use my second equation, which is 25 plus 10 times 4 minus 2, 25 plus 10 times 2, or $45. In example 8, it's asking us to graph the function using graphing technology. I have a hyperlink that's located in your blank notes that you can click on that shows you how to write a piecewise function into Desmos.com. However, I did graph this and I have a screenshot on how you enter it in, just as a quick reference here. So you need 3 lines in Desmos, 1 for each equation, and it's kind of written backwards. You'll first start off by putting the restriction in. I have x is less than or equal to 1, semicolon, and then the function itself, the equation, which is just in this case 0. In my second line, I have 1 is less than x, x is greater than 1, which is less than or equal to 4. I have my semicolon and then x minus 1 here. And then finally I have x is greater than 4, semicolon, and then my constant of 2. And then I like how in Desmos it's color coordinated, so you can easily see which graphs are part of which equation. The only down part is that it doesn't put the holes where they're needed. So just kind of be aware of that. You will have to either, if you're using the Desmos app, tap on that with your finger, or if you're using desmos.com, you will utilize you'll have to move your cursor over that location. So I have the constant of 0, y equals 0, when x is less than or equal to 1. And this will continue going left forever and ever. But as we approach 1 here, I'm going to have it equivalent here. But I also have a hole here with my blue line that will continue until I hit 4, which is included. And then when I hit the constant of 4, this line is excluded because it's greater than 4, not equal, but greater than 4. And then it'll remain constant going this direction. So you'll have to be careful that, notice when I took my screenshot, it didn't put the holes and such. But just kind of be aware of that as you're graphing with your graphing technology. And the last equation, just want to practice writing a piecewise function with 3 equations just to make sure we've got it. As another example, at Pierce College during the 2009-2010 school year, tuition rates for in-state were $89.50 per credit for the first 10 credits, $33 per credit for credits between 11 and 18, and for over 18 credits, the rate is $73 per credit. Write a piecewise defined function for the total tuition T at Pierce College between 2009 and 2010 as a function of the number of credits taken. Be sure to consider a reasonable domain and range. So the tuition is dependent upon how many credits that I am taking. Now, typically we take whole number of credits, but it is possible to have half and maybe even quarter credits. So I'm going to take that into consideration when I'm restricting my domain. But I'm going to have 3 lines, right? I have $89.50 for the first 10 credits. So $89.50 per credit for the first 10 credits. So if my credit load, I'm going to say between 0 is less than the number of credits, less than or equal to 10, because if I have 10 credits, I'm going to be charged this. Even if I have, let's say, half a credit, the 0, putting that there really helps define that portion, just in case there are partial amounts of credits that we can take. Then I have $33 when my credit load is between 11 and 18. So I have $33 per credit if my credit load is between 11 included and 18 included. And if I have over 18 credits, then I have $73 per credit if my credit load is greater than 18. Notice I said greater than 18, I didn't start at 19, because what if I had 18 and a half credits? Where would that fall? So anything over 18, even if it's 18.25 credits or 18 and a half credits, this takes care of it by starting at 18 for that last line, not including 18, because if I had 18, that would be the second equation. And now we've been able to kind of talk through all of the possibilities for the different amounts of credits that we can obtain. And this concludes our lesson on domain and range.